Hello, in this video we are going to see how to use the Verilog hardware description language to describe a simple digital circuit and to simulate it. We are going to use an Icarus Verilog compiler in a Linux system, but the process is very similar in any operating system that supports Icarus Verilog. You can find other videos explaining how to install the Verilog compiler. Okay, so now we want to design a simple voter circuit. A voter is a circuit that generates an output which value depend on the majority of the values at the inputs. So our voter will be something like this. Let's say we have 3 inputs. This is the output of our voter. Inputs will be A, B, and C, and output will be V, for example. So in our voter circuit, whenever 2 or more inputs are 1, the output will be 1. Okay. So before calling that design into Verilog, Verilog support different styles of calling, but one simple way to do it is that if we already know the logic function that our circuit does, if we calculate the logic function for the voter, we can do it, for example, using the method of the Karnaugh Map. We draw a Karnaugh Map. This could be for that function, so it would be 3 variables Karnaugh Map with inputs A and B here, C here. And we'll calculate function here. So in our voter circuit, the output will be 1 whenever 2 or more inputs are 1. So in this case, it would be 0. Here it would be 0, 0. Here we have 1, 2 inputs, 1. It's 1 here, 1 here, 1 here, 0 here, and 1 here. Okay. So doing the typical reduction minimization with the Karnaugh Map, we can implement it by using the prime implicants, using the midterms here, and from here we can deduce the function. Actually, understanding how to simplify logic functions using Karnaugh Map is not really necessary for the Verilog part, but in case you are currently doing a digital design course, you probably know the Karnaugh Map technique, so we can start from there. So from here, we see that our function, once minimized, can be described using these terms here. This term will be AB, A and B, or this term will be A and C, and this term represent the product B and C. So this is the logic function where the products are AND operations and the sums are OR operations. Now that we know the function, it's very straightforward to code it in Verilog. So now we need to create a new project. Actually, we are going to have it in a folder, right, called voter. And now we need to create a file here. To use Icarus Verilog, only works on the command line. It doesn't have a graphical interface. It's very simple to use, but you will need some way to organize your files, just like your standard file manager in your operating system. Then you will need a text editor. The standard text editor in your operating system is also fine. And then you will need a terminal to be able to run the Icarus Verilog from the command line. Okay, so it's important to have a terminal and to change the working directory to the folder you are in. So if you may have the option, as I have here, to open a terminal inside that folder, or you can simply search for the terminal window and then use the cd command to move to the folder. You can take the folder here and drop it on the terminal, so it will copy the path to the folder. So you put the path after the cd command, and now we are working in the folder folder. Okay, so here we have everything we need to manage our design. Now, into the folder I created, I have a new file here. I put some comments. And we start coding this example. Whenever you have to write Verilog code, you need to have some previous knowledge, and most of the time you will need to have at hand some reference with the Verilog syntax in case you have doubt on how to describe something. A good option is to use the Verilog reference from Sutherland. So if you search for Sutherland Verilog reference on the internet, one of the first links is this Verilog 2001 quick reference guide, which is a very compact reference that includes the syntax for mostly Verilog constructions. So it will not teach you how to use Verilog, but it is a good reference to solve your problems with the syntax. Okay. So now in this, I will save this file into my project folder. I will call this file voter.b. Now my editor has recognized that we are using Verilog, so we probably will have a nice syntax highlighting. And now let's start my code. So it's standard in Verilog to have the timescale directive, which sets the scale for time. 1 nanosecond and 1 picosecond are the standard in Verilog, so you will find it in most of the cases. It means that all times that I write are in nanoseconds, and the simulator will use 1 picosecond as the time resolution. Okay, and now in Verilog we start by defining a module. It's done with the module keyword. Our module will be called voter, and now we have to define the inputs and outputs. So basically what we do with this is that we put into code what we already had in our drawing. So the model declaration corresponds to the input and output description of our circuit. Okay. So we simply write the signals: input wire A, input wire B, input wire C, output wire B, which is the output signal. Okay. Now, Verilog doesn't need actually that you declare the type of the signal. The wire is one of the basic types, the one we will use here. If we omit the declaration, we will take the signal as wire, but I always prefer to explicitly declare the types. Wires are used for connections and for signals that are permanently assigned. So this is the right type to use in this example. Okay, now after the declaration, we need to say how I'm going to, what's the description of my circuit, how it's going to operate. So once I have the function calculated, as we have done before, we have the expression calculated, we can simply use that expression using an unconditional assignment in Verilog. It means I can describe the output as the permanent function it does, depending on the variables, which is a direct translation of the logic function I want in my function. So this is done with the assign keyword and simply assign signal B this result. Okay, so it will be A and B, or A and C, or B and C. So it's exactly the same expression we have, but here I'm using Verilog operators. Verilog uses the ampersand for the AND operation and the vertical bar for the OR operation. I will try to set the preferences. So we have okay, so we have okay, a slightly bigger font. So now that's it. And module will finish our module. So it's simply a circuit. The name of the circuit is filter, has 3 inputs, A, B, C, one output V, and the output is calculated by using that function. That's it. Okay. We save our design, and now we can compile that design with the Icarus Verilog compiler. This comment, first we check that we are with the ls comment. We can check that we are actually in the correct directory, and we also see our file we have just edited here. So with the terminal, I can execute the Verilog compiler. The name is iVerilog. I just put the name of the files I want to compile. I can put one file or many files. I execute the compiler. If we are lucky and there are no syntax errors, then the compiler will tell nothing, but it will generate a new file, this a.out, okay, which is a result of the compilation. So the compiler analyzes the Verilog code and generate a format that now can be handled by the simulator. If you make any mistake in your code, like for example, if you forget a semicolon somewhere and you execute the compiler, then you will have a syntax error and you will have to correct it. Okay, semicolon is missing here, so it realizes it's missing when it goes to line 12 and see that the assign doesn't belong here. So we correct the code, we compile it again, and now we would like to simulate this design to check if it's working properly. To do that, we need to write a test bench. And what a test bench is, actually a test bench is another Verilog module that we use to check the operation of another module. I will try to draw here, which is the idea behind a test bench. So we have our design here. And that's it. So now we have our voter module. It's a module like this, okay, with its inputs A, B, C, its output V, and this module is called voter. Okay, so that's when is a Verilog description where we are going to put one instance of my voter circuit. Normally, I will call this instance UUT from unit under test. Okay, and I will, in that new Verilog description, I will put a copy of the voter and then connect it to signals that generate input values that I will apply to the inputs. On my test bench, we also have some Verilog way to check that the output is correct. It may have Verilog code that automatically check that the output is correct, or it may simply print the results and so I can check the operation later. Okay, so to write a test bench, basically the idea is that I will put this box represents some Verilog code that will generate different values for the inputs of my circuit for A, B, and C. Okay, and we also have some Verilog code that will take the output and will do something with the output, that some check-in, just printing the results, whatever. Okay, and all these will be inside a new module, and this module will be our test bench. We can call the module simply test. Okay, as you see, this module will not have inputs or outputs because everything happened inside the module. Okay, my module will use signals to connect to my circuit under test. So we'll have to define some signals there that we can simply name in the same way they are in my unit under test, or you also may use a different name, but normally you will use the same name to avoid confusion. So this is basically the idea. Now I have to write the Verilog code for that, and I have to save this in a file. So we will put all these in a file named voter dash tb from testbench.v. Okay, this is like common practice that if we define a module that is called voter, we will describe the module in a file with the same name. Okay, and for the test bench we will use a different file because the test bench is a part of Verilog code that I will use only during simulation. So after the simulation, I know my circuit is correct, and I can use then my module in another design, and I only need the code of the file defining the code of the module. Okay, so this is the overall structure of a test bench. We will see now how it's encoded in with Verilog, but then we also need to plan how we are going to check our circuit. We need to generate these input signals ABC to test the voter. Now, as we will do in paper, we'll plan how to do it. Okay, so we'll have A, B, and C, and we can generate signals like this, for example, in order to test all the possible cases. For example, A can be 0 for some time. At some point, we will change the value of A to 1, and it will remain 1 here. The meantime, B will start being 0 as well, okay? And we can change B here in the middle. Then we change again. And at some point, it's not easy, we'll change it again. Here, for example. So the idea is that I will use waveforms for the inputs so that we have all the possible combinations of the signals when I test my circuit. Okay, so it's will be something like this. The drawing's not very good, but I think you get the idea. So this way we are checking all the possibilities, right? Because when we start, my inputs are 0, 0, and 0. Then we move to 0, 0, 1, then 0, 1, 0, and so on. Okay, so with these kind of signals, we will be checking all the possible combinations of the inputs, and then we can say the simulator to save the value of V and check what happens. What I expect is that V will be equal to 0 all the time except when 2 or more inputs are equal to 1. So I expect to see something like this, and then something like this. Okay, so whenever 2 inputs or more are 1, here I'll expect to see this one. I will make the simulator to calculate this. Okay, then let's encode it using Verilog. To do that, we will create a new file. We'll save that file. We call it voter TV. And now, like before, we set the standard timescale. Now we start our module. We will simply test, okay, with no inputs or outputs. And we'll start the definition. So we need signals to, now we declare the signals, in the internal signals in our test module to connect to my circuit under test. So these are wire signals A, B, and C. Okay. I can put some comments here. I also have the output signal here, V. I put some comment here. Okay, and now in my description, I have to put a block, a voter block. So I simply do it like that. Say voter, it means I want to put a copy of a module voter. Now the name of the instance will be UUT. So I take a voter, I call that copy UUT, and now we connect it like that. To make the connection, I put a dot, the internal signal of the module voter, and now in parentheses, the external signal I want to connect to. Okay, I put the same name here, but this A here refer to this external signal here, to the signal in my test bench. This A here refer to the name I've given the signal inside the voter module. Okay? I do the same for the rest of the signals. C, B, dot B connected to B. Okay, semicolon. So far we have this describe this. Okay, we have put a copy of the voter, we have defined these input and output signals, and now we have to describe how signals change with time. Okay, we can do it with the procedural description, where we can simply assign signals its values. Okay, because we are going to use a procedural description, we need to correct something, which is we need to change these signals to type reg. Reg is the type that we use for variables in Verilog, and variables are the signals that we can assign into a procedural description. The typical procedural description in a Verilog test bench is the initial, because this is an algorithm that will be executed just once. It will not be repeated. Okay, so this is the good choice to control my simulation. Okay, so we can start by setting all the signals to 0. So I simply put A equal to 0, B equal to 0, C equal to 0, as in the waveform we want to write there. Okay, it's input initialization. Okay, now next thing, I can tell the simulator that I want to generate results. It's done with some Verilog directives. I'll try to remember. Down file is the where we are going to store Verilog results. Okay, so a standard way to do it is use the standard waveform file, which is VCD, and we name the file as we have named the file for the test bench. Okay, so that file tells Verilog where to store results, and downwards tells Verilog which signals we want to store to save. Okay, so I think the syntax is something like this. Downwards means save the waveforms. 0 means here all the signals at all levels of module test. Okay, so with these two Verilog functions, the simulator will know that we want to save the waveforms for our signal, so we can view our waveforms with another program, with the waveform viewer. If we just want to print results in the terminal, we can use the display command. Okay, but this way we can check in a waveform viewer. Okay, now we want to just generate signals like this. So we will take this time, this period of time when C changes, as some unit of time, like 10 nanoseconds, for example. Okay, so we will write in Verilog all the changes we want our signals to make. So we will start our simulation, wait 10 nanoseconds and make C equal to 1. Then we'll wait 10 nanoseconds, make C equal to 0 and B equal to 1, and so on and so forth. So let's do it. Okay, I will move it here so we can see we want to do. And let's write this. Okay, so after 10 nanoseconds, this is the construction with the to tell the simulator to wait for 10 nanoseconds. I make C equal to 1. Okay, then we wait another 10 nanoseconds. These are additional to the current simulation time, and then we make B equal to 1 and C equal to 0. Okay, 10 nanoseconds later, now C is equal to 1 again. Okay, so 10 nanoseconds later, we make B equal to 0, and I think that case will be A is equal to 1, and now B is equal to 0, C equal to 0. Okay, so we describe the changes we want in our signal. Of course, we could put all the signals, all the values, if we find it easier to do. Okay, we can say A equal to 0, B equal to 0, C equal to 1. Actually, we can write we can describe those signals in many different ways. Okay, this is just only one option. It's simple to code, maybe not the best option. We may use different thing, but it's a very straightforward way to do it. Okay, now C will be equal to 1, next change, and basically now we repeat. Okay, next change will be B equal to 1, and C comes back to 0. Next change, C will be 1 again. And here we have tested 1, 2, 3, 4, 5, 6, 7, 8. Now we have all the possibilities. Okay, we are ready, our signals are already gone through all the possibilities. So we now just wait some time more, let some time to for the last input combination to stay in my simulator, and after some time, let's say 20 nanoseconds, we call the finish simulator function. We will end my simulation, right? And that's it. That should be enough. Basically, we end our module description. And this is our test bench. Okay, so I simply hope you can see the relation, okay, that we have simply convert the intended waveform to check our circuit into Verilog code. Okay, so now we save our design, go to the terminal again. Now we see we have the voter test bench in our folder, and now we compile everything together. I Verilog, and I put the names of both files. Okay, we'll execute. There are lots of syntax errors, so we make some mistake. The important thing is to check the first error in the file, right? And start working from there. So yes, okay, the problem is that inside this initial block we are executing several instructions here, so we need to surround it by block delimiting, code block delimiting keywords, okay, begin and end. So we have solved that. We'll repeat simulation, the code compilation again. Okay, so we have no mistakes now. Okay, so now this has generated the a.out file that we can simulate. The simulator in Icarus Verilog is the command vvp, and we simply give the command the code generator by the compiler. We execute that, okay, And now the compiler just tells that has generated a dump file here. And this is our dump file, the voter TV VCD as we said here. And this is a type of file with the waveforms result. To open that file, we need a waveform viewer. We have also installed a waveform viewer, which is name is Gtkwave, so we can open it from here, from the file. And okay, now what we have to do is to add the waveforms we want to check. So here we see the hierarchy of my design. I have the test module, which is our test bench. Inside my test bench, I have the input signals, the internal signals A, B, and C, and the V signal. But inside my test bench, we can see we have the UUT, the unit under test, and these are the signals internal to the UUT, okay? They have the same names or are different signals. We can use these ones or these ones to check what happens internally or externally. But in our case, we use the signals in our test bench. We can select all of them and we append to the waveform viewer. Once we do that, we use the full zoom button here to see all the signals at the same time. So here we can see if we have done it correctly. I think so, because you see our outputs are 0, 0, 0, A, B, and C. C changes to 1, 0, 0, 1, 0, 1, 0. You can move, click with the cursor here and check the values. And now we need to check if the output is correct, okay? And we can see that it's correct for the values, I think. In this case, we have two ones, the output is 1, 1, 1, the output is 0, here is 1, here is 1. So we can see that it corresponds to what we expected from our design, okay? So basically this is the design process, okay? So to wrap up, you need to somewhere to manage the files in your project. You need a terminal to execute the compilation and simulation of your code, and then you need a text editor to edit Verilog code, and that's it. Okay. Okay, now imagine that you need to modify something. I want to modify my test bench, for example. I want to modify it somehow. Like say we want to start with all input set to 1, okay, and do the simulation in this other way, okay. So we change my test bench in some way, we save the code, and we simply go and repeat the whole process, okay. We can use my terminal. Normally, if you use the up arrow in your keyboard, you can recover all commands. So I can simply recover the compilation program, compile it, now recover the simulation program, I simulate the design again, and if I want to refresh, we don't really need to close and open the waveform viewer. We can use in here the option to reload waveforms, okay? So we simply reload the new results from simulation, and here we see that change. Now we start simulating in 1, 1, 1 case, okay? Sometimes you want to rearrange your signals in your simulation. You may want to put the output at the top of it, and you may want to change the data format of your signals when you have more complex signals. If you configure the way you want to view your waveforms here, you can save that format in a file. Okay, so you can simply go here and use the option write save file, and it will save a file. I would say voter db.gtkw. Okay, this is the extension for Gtkwave save files. So save that, and now I can close my simulator, and now when I open the file again with Gtkwave, okay, yes, when we open our file again, we don't need to go and configure the viewport again. I can simply read my save file with my waveform configuration, and that's it. Okay, so this is all with our little example. If you want to take a look to more Verilog examples, you can check my Verilog course in GitLab. Here you have the address where you can find many Verilog examples corresponding to an introductory digital design course, where you can check those examples. Simply go to the Verilog folder and follow the units, starting at the first unit and at the first lesson. And what will you find there? Let's say here, for example, what will you find there? It's in every unit is the code, including lots of comments in the code explaining all what happened in the example. Okay, so that's it. Thank you.